We will now discuss yet another important concept in physics, that is the concept of energy. Energy is something that we use in our everyday life. Now, what does energy means in a layman's language? Have you ever heard somebody saying, "Oh, I feel I have no energy today"? And I heard my daughter saying the other day, "Oh, I need some sugar." Apparently sugar gives you energy, I think. What does that mean when you say you have no energy? It means I don't feel like getting up. Well, if you want to get up, that means you are doing work, you are lifting your weight. So when you say you have no energy, what you're saying is that you don't feel like doing any work. That means energy is related to work. Is that right? In fact, energy is required to do work. If you have no energy, you cannot do work. And so, a simple definition of energy is the ability to do work. If you are able to do work, then you have energy. If you are unable to do any work, then you have no energy. Now, what is the unit for measuring energy? Since we defined energy as the ability to do work, isn't it reasonable that we measure energy in the unit of work? Yes, I think so. So, energy is measured in the same unit as work. And what is that unit? It is the joule. Energy is measured in joule. 1,000 joules is a kilojoules. 1,000,000 joules is a megajoule, and so on. Okay, let's consider a book of mass m gram on the floor. Now this is the floor level. We have a book of mass m kilogram. Tell me, what is the weight of this book? The weight of the book is mg Newton. And what is the direction in which that weight is acting? It is acting vertically down. So when the book is on the floor or on the table, the earth is pulling it with a force of mg Newton. Now tell me, what is the force required to lift this book without causing an acceleration? In other words, the force you require to lift that book without causing an acceleration is the force that is needed to balance so that the net force is zero. What is that force? Since there is no acceleration caused by lifting, there should be no net force on the book. If there is a net force on the book, that net force will create an acceleration. Since we don't need an acceleration, all we need to do is to make the net force equal to zero. What do? Therefore, in order to lift this book, you need to apply a force F upward so that F minus mg equal to zero, or the magnitude of that force is equal to that mg. So F minus mg equal to 0 or F equal to mg. In order to lift any object, you need to apply a force equal to its weight upward. Well, that's a very simple concept, is that right? Now here I have a bag sitting on the table. If I want to lift it, what is the force I need to apply on it? It's a very heavy bag. Its weight mg is acting vertically down. In order to lift it without causing an acceleration, well, remember that exists only in theory. In practice, the moment I lift it, I am causing an acceleration. But at the moment, I don't want you to consider that acceleration. In order to balance the force, what I need to apply is a force upward equal to its weight. I am applying a force F upward, which is equal to the weight of this bag. In order to lift any object, I need to apply a force equal to its weight. Now here I have a 500 gram, about 4.9 Newton sitting on my hand. Now what is the force I need to apply to lift it? Is 4.9 Newton. Okay, let's now use this to describe two types of energy. This concept can be used to explain the concept of potential energy. We now know that an object of mass mg, in order to lift that object, you have to apply a force F equal to mg on that object. So force F equal to mg is required to lift the book without causing an acceleration. Now let this force lift the book through a height h. Alright, we are going to apply this force F and lift this book through a height h. Tell me, what is the work done by this force? The work done by this force now is this force multiplied by that displacement, that is h. So the work done is force multiplied by that distance, and the force equal to mg, and therefore the work done on this book to raise it to a height of 2 meters is mgh, to raise it through a height of h meter. The work done is mgh. Well, this is the same as saying that the energy used in doing this work is mgh. If I have this object of mass m lying on the floor, it's lying on the floor, and I'm going to lift it through a height h. I'm going to apply a force, and that force equal to mg, and that force mg is lifted through a height h. That means I have now used up part of my lunch energy to do this work. How much energy did I use? I used mgh, that force multiplied by that height. So the amount of work done to lift this object through a height h is the same as the energy used in doing this work. Now remember, work done and energy used up are the same thing. When I'm doing work, I'm using up energy, right? If I suddenly want to jump onto that table, I have to do a tremendous amount of work. That means a lot of energy is going to be spent on that particular activity. The energy in turn allows the book to do work when you stop supporting it. Now look at this. I have done work on this object. How much work did I do? I did an amount of work mgh. Now if I let it go, it can do work. Well, what kind of work? Well, oops, my foot. Did you hear what happened? It went and did work on my foot. Well, I didn't really let it fall on my foot, but imagine if it did fall on my foot, it would have done work on my foot. So that means when you raise an object through a certain height, you have now placed that object in such a way that it is now able to do work. We say it has the potential to do work. When it has the potential to do work, it has potential energy. Well, So the book placed at a height h has a certain amount of energy stored in it. This energy is called the potential energy. In other words, that book has now the potential to do work. It has potential energy. If you look around, we use a large number of circumstances where energy gets stored so that that stored system has the potential to do work. Can you think of some of the systems where energy gets stored so that it has the potential to do work? Well, you are actually watching one example. I stored energy about half an hour ago. I had a sandwich. Well, I have stored energy. And that means I am able to do work. That stored energy is actually a form of potential energy. There are many other examples. Let's take a look at a couple of those examples. An example that is not very difficult to understand is stretching of a spring. When I do work on the spring, look at that, I'm going to apply a force and move that force. Means I'm doing work. Now, you know, if I take my hand off, it is going to do work on me. Oops. Did you see how it is able to do work? Now, a stretched spring has potential energy. There is energy stored in it. Well, if I want to get this pen onto a student over there who did not bring a pen today, look at that. All I'm going to do is I'm going to do some work in stretching this elastic band, and you can see the pen went all the way to the other end. It hit me also. Well, a stretched elastic band has potential energy. It is capable of doing work. Now, if you look here, I have a spring-loaded gun. Now, I'm going to do work on this. Look how I'm going to do work. I'm going to apply a force and allow that force to move. Well, apply the force and allow that force to move. And this system now has potential energy. It is capable of doing work. Now, look at the work it is going to do now. There you are. You can see it did work. So, systems where energy can be stored, those systems have potential energy. So tell me, what is the potential energy of an object that is placed at a height h? The potential energy of the object placed at a height h is the amount of work you did to place it there. And how much was it? You remember? mgh. If you raise an object through a height h, its potential energy is mgh. That means if you let it go, it can now do that much amount of work. It has the potential to do that much amount of work. So, potential energy is represented by the letter uppercase U, and of course it is measured in joules. Whenever you want to represent potential energy, we will use the uppercase U. What is the potential energy of a book placed at a height h? The potential energy of a book placed at a height h is a measure of the work done in order to place it at that height. And that is U equal to mgh. In fact, the potential energy of any object that is placed at a height h is mgh. Alright, tell me, if I stretch a spring, what is its potential energy? What is the potential energy of a stretched spring? Well, We talked about the amount of work done in stretching a spring. What is the work that you need to do to stretch a spring? It'll be 1/2 kx squared, is that right? And when you do an amount of work 1/2 kx squared, it gets stored in the spring as its potential energy. So potential energy of a stretched spring is 1/2 kx squared. That is an important information. We will be using it as we move on. Let's now talk about conservative and non-conservative forces. Another important concept in physics. Now, weight of an object is a measure of the gravitational force on it. Now, the gravitational force on the book is negative mg. Why do we call it negative mg? Gravitational force is directed downward. Now, the amount of force that you need to apply to lift it is positive. You apply it upward. But the gravitational force on the book, which is its weight, is negative mg, which is directed downward. Well, here again we have the book. Its weight is mg acting vertically down. Now remember, when we have indicated the direction as downward, you will not then use the negative sign. The negative sign simply tells you that that force is directed down. Now, what is the work done by the gravitational force when the book is raised through a height h? Now, you must distinguish between the work done by the applied force. What we did in the previous slide is to calculate the work done by the applied force in racing through a height h. And that is F times h, where F equal to mg. Okay, now tell me, if negative mg is the weight of the book, which is the gravitational force on the book, what is the work done by that gravitational force when you raise the book through a height h? When you raise the book through a height h, this gravitational force, which is negative mg, has been moved through a height h, or negative mg is displaced by h meter. Therefore, work done by gravity on the book is negative mgh. The work done by the applied force on the book is positive mgh. But the work done by the force of gravity on the book is negative mgh. Now, if you allow the book to fall, this gravitational force, negative mg, will be displaced by negative h. Is that right? Yes. When the book is now allowed to fall, well, here is my book. If now the book is allowed to fall, this negative mg is going to be displaced through a distance negative h. Displacement is downward. There you are. It's negative h. So what is the work done by gravity in this case? The force negative mg has been displaced by negative h. Therefore, the work done in this case will be negative mg times negative h, which is positive mgh. Well, one more time. The work done by the force of gravity when the book is raised up through a height h is negative mgh. Alright? When the book is allowed to fall, the gravitational force negative mg is displaced through a distance negative h. Therefore, the work done during that time is negative mg times negative h. That is positive mgh. Therefore, what is the total work done by the force of gravity for the entire trip? The work done by the force of gravity in raising the book is negative mgh, and the work done by the force of gravity while the book is falling through the same height is positive mgh. Therefore, the total work done for the entire trip is negative mgh plus mgh equal to 0. Now, this is a very important concept. I want you to understand this because we're going to use it here and also in the next semester physics. Very important. A force is conservative if the total work it does on the object is 0 when the object is moved around in a closed path. Now, what is the meaning of a closed path? Suppose this is the beginning. I raise the object through a height h and leave it. The force of gravity, I'm not talking about the work done by the force I applied. I'm talking about the work done by the force of gravity. The work done by the force of gravity for the first part of the journey is negative mgh. While the object is allowed to fall, the work done by the force of gravity is positive mgh. The total work done is 0. So, a conservative force is a type of force where the total work done in a closed path is 0. Now, therefore, we say the force of gravity is a conservative force. Now, can you think of any other force which is a conservative force? Well, when I stretch a spring, you know that the spring will pull me back. Just like when I lift an object, the earth will pull it back. When I stretch a spring, the spring will pull me back. And the force applied by the spring is called the restoring force of the spring. Now, the restoring force of the spring is a conservative force. The work the restoring force does while I stretch it is negative. When I let it go, the work it does is positive. The total work done in a closed path is 0. And that is the definition of a conservative force. So gravitational force is a conservative force. The restoring force of a spring is a conservative force. Well, if the gravitational force is a conservative force, the restoring force of a spring is a conservative force, can you give me an example of a non-conservative force? Is there an example for a non-conservative force? Now, think of a surface moving on another surface in a closed path. And one of the forces involved in here is the force of friction. Is the work done when the object is moved in a closed path by the force of friction 0 in this case? No. The work done when the work done by the force of friction when the object is moved in a closed path is not 0. Therefore, force of friction is a good example of a non-conservative force. So you must be able to distinguish between a conservative force and a non-conservative force. Well, good examples of conservative forces are gravitational force and the restoring force of a spring. And a good example for a non-conservative force is the force of friction. Let's look at the restoring force of a spring. When a spring is compressed by a force F, the spring applies a force in the opposite direction, and it is that force that we call the restoring force. So when you try to compress the spring, applying a force towards the right, the spring will apply a force in the opposite direction, and that is what we call the restoring force. Now, the work done by the restoring force, if now the spring is compressed by a distance x, the work done by this restoring force, which is negative F, will be negative F times x, and you know that will be 1/2 kx squared. So work done by the restoring force of the spring is negative 1/2 kx squared. Now, once the spring is compressed, if you now remove the external force, what will happen? The spring will jump back, or the restoring force will now restore the spring to its original position. Now, the amount of work done what will be the amount of work done at that time? The amount of work done to compress the spring by a distance x, the work done by this force, that means the force applied by the spring called the restoring force. The work done by the restoring force is negative 1/2 kx squared. When the applied force is removed, the restoring force stretches the spring back to its initial position, doing an amount of work, how much? W equal to 1/2 kx squared. So while compressing, the work done by the restoring force is negative 1/2 kx squared. When the external force is removed, the work done by the restoring force is positive 1/2 kx squared. Therefore, the total work done by the restoring force is negative 1/2 kx squared plus 1/2 kx squared equal to 0, which indicates that the restoring force of a spring is a conservative force. I want you to pay special attention to this particular statement I'm going to discuss now. The tendency of a conservative force is to decrease the potential energy. What does that mean? The tendency of a conservative force is to decrease the potential energy. Can you visualize what that means? Well, I think I need to explain that. Now, let's consider a basketball sitting on the floor. There, it's sitting on the floor. Now, we say that the earth and the basketball, these are two objects. One is the earth, other is the basketball. Let me see if I can draw that for you. Now, here is the earth and here is the basketball. We say this system, which is called the earth, the basketball system, there are two objects. Now, this system has a potential energy U. What happens when I lift the basketball up? Look at that. I'm lifting the basketball up. What did I do? I increased its potential energy. So, if I take this basketball away from the surface and keep it there, I am increasing the potential energy of the system. So tell me, when do you have the potential energy of a system the least? When they are closer together or when they are farther separated? The potential energy of two objects is the least when they are very close together. So when the basketball is on the ground, the Earth's basketball system has the least potential energy. When I move the basketball up, I do work on it, increasing the potential energy of the system. So, what is the sentence which I just read for you? The sentence is, the tendency of a conservative force is to decrease the potential energy. What does that mean? You see, when I lift the basketball, the force of gravity tells the basketball, hey, you, come back. Isn't it? The moment I leave, it goes back. So what is the tendency of a conservative force? The gravitational force is a conservative force. That means if I raise the basketball, the conservative force, which is the earth, the gravitational force, does not like it. It wants this ball to be back on the ground so that their potential energy is zero. The tendency of a conservative force is to decrease the potential energy. Now look at this, the spring. When I stretch it, its potential energy increases. Now, you know when I stretch a spring, the restoring force of the spring is pulling it back. It says, come back. Let's have least potential energy. The restoring force of the spring is a conservative force. The tendency of that conservative force is to decrease the potential energy. A very important concept. So let me say that again. What is the tendency of a conservative force? A conservative force always wants to keep the potential energy of systems the least. Earth attracts all other objects towards its center so that the potential energy of the Earth object system will be the least. The tendency of a conservative force is to decrease the potential. So the gravitational force pulls an object towards the ground where the potential energy is the least. A compressed spring has potential energy U equal to 1/2 kx squared, and the restoring force of a spring tends to restore the spring to a state of zero potential energy. Therefore, work done by a conservative force always causes a decrease in potential energy. And whenever you want to denote a decrease, we will use a negative sign. Is that right? So, the work done by a conservative force, if W is the work done by a conservative force, its tendency is to decrease the potential energy. W equal to negative U. Well, does that make sense? Yes, the work done by a conservative force always decreases the potential energy. Work done by a conservative force equal to negative of the potential energy. Now, this is the same as saying that the increase in potential energy equal to negative of the work done. Is that right? If the work done is a measure of the decrease in potential energy, then the increase in potential energy equal to negative of the work done. Potential energy is the negative of the work done by a conservative force when an object is raised from a height h1 to a height h2. And so, in calculus, we can write it like this. Potential energy equal to negative of, look at that, negative of the work done. Work done by what? Work done by this conservative force, which is negative mg. So potential energy U equal to negative of the work done by the conservative force, which is integral h1 to h2 negative mg dy. And that will be mgy from h1 to h2, or you can write it as mg times h2 minus h1. If this h2 minus h1 is equal to h, then potential energy equal to mgh, or we can now call it mgy, because h2 minus h1 is the distance y through which the object is raised. So potential energy equal to mgy is the same as the first equation that we obtained, potential energy equal to mgh. Let's now talk about kinetic energy. Another form of energy is kinetic energy. What does kinetic mean? Kinetic is related to motion. So kinetic energy is energy related to motion. Work done on an object can produce motion on the object. That means a moving object has energy. A force F acting on an object of mass m displaces it through a distance x, giving it a velocity Vf equal to v. Let's picture that. We have an object of mass m here, and a force F is acting on it. Well, remember, a force acting on an object will produce an acceleration on the object. And if there is an acceleration, its velocity will change. So the object now moves to a distance x, acquiring a velocity v when it comes here. So the initial velocity of this object is 0. When the force F acts on it, it moves through a distance x, acquiring a velocity v. Alright? Now, you have this equation, everybody knows this, v squared equal to v0 squared plus 2ax. This v is the velocity it acquired in moving through a distance x. And v0 is 0. Can you solve for a, the acceleration? Well, we have v squared equal to 2ax. And so let's solve for x. X equal to v squared over 2a. Alright? What is the work done by this force? Work done by this force on this particle is the force multiplied by the displacement. So we can say W equal to F multiplied by X. And now we can replace this F by MA. Is that right? It is the acceleration produced by this force that is responsible for displacing the object through a distance x and giving it a final velocity v. So we can say F equal to ma, and x can be replaced by this quantity v squared divided by 2a. So the work done on this object in giving it a velocity v is W equal to F times x. That will be ma times v squared over 2a, and you can see a and a will cancel, and that will be 1/2 mv squared. Now listen to the statement I'm going to make here. The work done on an object of mass m, in order to give it a velocity v equal to 1/2 mv squared. And it is this quantity we call the kinetic energy of the object, because this is a measure of the work done on the object to give it that velocity. That means that work has been done on that object. It has now that much of energy. That means if you now try to stop it, it will do work on you. If you stop it, it will do this much of work on you. And that is why a bullet kills. A bullet moving with velocity v has a kinetic energy of 1/2 mv squared. If you stand on its way and stop it, all this energy is going to be spent on you. It will do work on you. So how do you define kinetic energy? So this energy that is stored in a moving object is called kinetic energy of the object. And we will represent kinetic energy by the uppercase K. Although in many books and in many parts of the world, kinetic energy is represented by the uppercase T. Now, we're not going to do that. It's easier for us to call it uppercase K. So, our kinetic energy will be represented by the uppercase K. Potential energy will be represented by the uppercase U. Okay. So, K equal to 1/2 mv squared. And in a simple sentence, you can define kinetic energy like this. Kinetic energy is a measure of the work done in giving an object a velocity v. Also, you can say a moving object has kinetic energy, which is a measure of the work it is capable of doing in coming to rest. It is also measured as the work done to bring a moving object to rest. If you try to stop a moving object, it will do work on you. Try to stop a moving train, then you know the ferocity of the work it can do on you. Let's now talk about the law of conservation of energy. A very important law in nature, law of conservation of energy. Law of conservation of energy states that total energy in the universe is a constant. Energy can change from one form to another. Potential energy can change to kinetic energy, and kinetic energy can change to motion, to other forms of energy like electrical energy. There are many forms of energy, but most of them can be classified as either potential or kinetic. So potential and kinetic energies are called mechanical energy. Mechanical energy. Just to distinguish it from other forms of energy called chemical energy, electrical energy, and so on. So this means that the next change in energy must be zero. The next change is zero. If delta U is the change in potential energy and delta K is the change in kinetic energy, then delta U plus delta K equal to zero. The total amount of the change in energy will be zero. In other words, the total energy in the universe will never change. There will be a change in the potential energy, there could be a change in the kinetic energy, but a change in one form comes at the expense of the other, so that if you add all the changes, the total change will be zero. That is the essence of the law of conservation of energy. The gain in one form of energy comes at the expense of the other, so that the next change in energy is always zero. Let's talk about a ball that is 1 kilogram mass raised through a height of 5.1 meter. Now here, there you go, the ball is raised through a height of 5.1 meter. The mass of the ball is 1 kilogram. Can you calculate the work done to do this? The work done to raise this through a height of 1 meter is mgh. Is that right? The work done is mgh. 1 kilogram times 9.8 meter per second squared times 5.1 meter, that is 50 joules. In order to raise this 1 kilogram mass through 5.1 meter, we did an amount of work 50 joules on it, and this is a measure of the potential energy of the ball. Alright, so we say U equal to 50 joules at this position. When the ball is placed at the height, its potential energy is 50 joules. Since the ball is at rest here, its kinetic energy is 0. Is that right? We raise the ball and it is at rest there. Its kinetic energy is 0. So when the ball is at this position, its potential energy is 50 joules. Kinetic energy is 0. So what is the total energy at the top? The total energy is potential energy plus kinetic energy, that is 50 joules. Okay, what happens if the ball is now allowed to fall to the ground? If you now leave the ball, there it goes. It has fallen to the ground. Now, all the potential energy it has at the top becomes kinetic energy at the bottom. Is that right? The reason why this ball, when I drop on my foot, it will do work on my foot, because all the potential energy it has now here will become kinetic energy just, see that, just before it hits the ground. Okay. Now, that means at the ground, all that energy, its kinetic energy is now 50 joules. Its potential energy on the ground is 0. Therefore, the total energy will be 50 plus 0, that is 50 joules. Let's calculate that. In falling through a vertical height h, it acquires a velocity v, is that right? If it falls through a height h, it acquires a velocity v. Can you write an equation for that v? Well, v squared equal to v0 squared plus 2gh. Is that right? Yes. So v squared equal to v0 is 0. So v squared equal to 2gh. And so v squared is 2 times 9.8 times 5.1. That is 100 meter per second squared. Or kinetic energy will be 1/2 mv squared. That will be 1/2 times, the mass is 1 kilogram, and v squared we just showed is 100 meter per second squared. Now look at this. The kinetic energy when it reaches the bottom will be 50 joules. That means all that potential energy got converted to kinetic energy there. The total energy at the bottom is potential energy plus kinetic energy, and that is 50 joules. The total energy at the top is 50 joules. The total energy at the bottom is 50 joules. Just now consider an intermediate position. Consider the ball at some intermediate position when it has fallen through a vertical height of 2 meters. Alright, let's allow it to fall through 2 meters. There you are. Let's calculate the potential energy and the kinetic energy at this position. Well, while falling through 2 meters, it acquires a velocity v. Can you write down an equation for that velocity? V squared equal to v0 squared plus 2gh. v0 is 0, and therefore we have v squared equal to 2gh. 2 times g times h. That means v squared when it falls through this height is 39.2, and therefore what is the kinetic energy? The kinetic energy will be 1/2 mv squared. 1/2 times m is 1 kilogram, and v squared we calculated 39.2. Now I have a small error here. V squared is not measured in joules. It is meter per second squared. So cut that off and write it as meter per second squared. Kinetic energy is 1/2 mv squared, 1/2 times 1 kilogram times v squared is 39.2, and that is 19.6 joules is the kinetic energy. So in falling through 2 meters, this 1 kilogram ball has now acquired an amount of kinetic energy, 19.6 joules. Now, what is its potential energy at this position? What is the height now? The height is now 5.1 meter minus 2 meter, that is 3.1 meter. The object is now at a height of 3.1 meter. What is its potential energy? Potential energy is mgh. 1 kilogram times 9.8 meter per second squared times 3.1 meter, that is 30.4 joules. So at a position 2 meter, after the ball has fallen through 2 meter, it has acquired a kinetic energy of 19.6 joules, and at that position it has a potential energy of 30.4 joules. What is the total energy at that position? The total energy is potential energy plus kinetic energy. That is, add the potential energy to the kinetic energy, you get 50 joules again. In other words, when you raise the ball and allow it to fall, the total energy at any position will be the same, 50 joules. That is the essence of conservation of energy. Energy keeps changing from one form to another, but the total energy always remains the same. The energy that we get from the sun gets converted to many other forms. Look at that. The heat from the sun is used to give potential energy to water vapor. It rises and we get rains, we get water collected. Water collected in a dam has potential energy. If you allow that water to flow, that flowing water has kinetic energy, and that kinetic energy can be used to turn turbines to produce our electricity. Look at that, how energy from the sun is now gone through these conversions until we get electrical energy. And electrical energy can be converted to light energy. Look at the way we are able to see because of that. And electrical energy can be converted to sound energy. And well, you are able to use this medium to do this course because electrical energy can be converted to many other useful forms of energy. But remember, always the conservation of energy is obeyed. The net change is always zero. Energy can be converted from one form to another, but the net change in the energy is always zero. Irrespective of the position of the ball, the total energy is a constant. You see, the law of conservation of energy is a beautiful concept. It is that concept that keeps us alive, that keeps the universe alive. In fact, the whole universe is a hub of energy. You see, the Chinese word for physics is the dance of energy. The whole universe is a great big dance of energy. Energy gets converted from one form to another continuously. In fact, the whole of the universe is actually a big, great, big pot of energy. And the universe that we know is simply a small bubble in there, a simple bubble. You see that? A bubble comes and that is what we are, the whole of the universe. And that bubble can burst and form another bubble. The big universe is simply a great big dance of energy. Energy continuously gets transformed from one form to another. You and I are part of that small bit of energy, and we will eventually get back and become part of that energy. We are all part of that great big soup of energy. Isn't that wonderful? And physics gets very interesting and fascinating when you want to study that great big pot of energy. In fact, in trying to answer the question, what is that everything that we see? What are we made of? What is everything in the universe made of? It takes us to the very core of this question. Everything is made of little strands of energy called strings. In fact, the whole of the universe is a great big haze of that string. And depending on the resonance pattern, it can change different shapes and forms. And universe is a continuously changing, boiling pot of energy. Well, at the moment we have no time to talk about it, so let's now go and discuss the concept of work energy theorem. Work energy theorem is a consequence of the conservation of energy. What is conservation of energy we talked about? Conservation of energy tells us that the net change in energy is always zero. Work energy theorem is a consequence of the law of conservation of energy. Alright, now here I have a slide. A child is sitting on top of that slide, and the slide is at a height h from the ground. The girl on the slide has a potential energy U equal to mgh. If she now slides down, she gains kinetic energy at the expense of potential energy. Now, so at the bottom, actually all that potential energy will become kinetic energy, so that delta U plus delta K equal to 0. The net change in the energy equal to 0, or all the potential energy lost will become kinetic energy. But in actual fact, all the potential energy lost may not become kinetic energy. Well, if all the potential energy gained becomes kinetic energy, this girl will break her jaw by the time she lands, because her speed will be enormous. There is some energy lost in work done against a non-conservative force. You see that? There is friction here, and some energy is used in doing work against that friction. And therefore, it is more convenient to say in this case that there is a net change in energy, and that net change in energy is used in doing work against friction, against the non-conservative force. Well, let's talk about that. But in practice, some energy is used in doing work against the non-conservative frictional force as she slides down. That means we will now be able to amend the equation like this. For all practical purposes, we would say the net change in energy is a measure of the work done against friction. The net change is a measure of the work done against friction. And this statement is what we call the work energy theorem. And it's a very important statement. What does the statement say? The net change in energy is a measure of the work done against non-conservative forces. Well, we will use this concept to solve problems in the next part of the lesson. Before I close this lesson, I would like to show you an application of the conservation of energy principle. Well, you're all familiar with the roller coaster. Now, when you want to ride the big Kumba, is that right? Where is that? In Tampa, is that right? Now, the car is taken to a great height, is that right? That's when the energy is used. Work is done to drive the car up, and then you let it go. What happens? Well, it really didn't do very well, did it? Well, you can see the potential energy it had become kinetic energy at the bottom. The kinetic energy is converted to potential energy, and it will continue. Let's see one more time. If I leave it here, there you are. So the continuous conversion from potential energy to kinetic to potential, and the system will continue. And that is a great application of the law of conservation of energy. Alright, I'm going to stop this part of the lesson here. I will see you for solving problems using these concepts in the next part of the lesson.